Let me welcome the first speaker of the day, Håvard, who is a PhD student within the Institute for Theoretical Astrophysics in Oslo, and is going to talk about noise estimation. Thank you, Håvard.
Thank you. I'm Håvard Ihle. I'm a PhD student here in Oslo, and I'm going to tell you about the noise modeling that we've been doing here in the BeyondPlanck team. So just to remind you a little bit of where we are and where we're going. So yesterday, Hans Christian talked about the whole idea of BeyondPlanck, which is to have a complete statistical model that incorporates everything in the analysis pipeline. So both gain and bandpass and other instrumental variables, and then foreground components, spectral indices, everything in one complete statistical model. And then we iterate and iterate in this model to get a better and better solution. And the way we do that is by using Gibbs sampling. So we basically fix all the parameters, all the free parameters except one, and then we sample that one from the conditional distribution, conditioning on all the other parameters. And then we go on to the next one and to the next one. And today we're going to start go into the details a bit about how we actually do these different steps. And for this talk, I'm going to talk about sampling the correlated noise and the corresponding noise parameters. And so the parameters of the noise power spectrum. And if you want to see the more details about this, you can see this paper that came on the archive this week. Okay, so here is our data model. If you remember yesterday, Hans Christian showed like a very large and complicated data model. But the nice thing about Gibbs sampling is that you only have to do one step at a time. Like for us now, when we're dealing with the noise, we assume that the gain and the total, like all the sky signal, all the complicated things that are in here, we assume that that's fixed. So what we do is to define this signal subtracted data. We just take the raw data in the time domain and then subtract out the total signal times the gain in time domain. And what's left over should then be just the white noise and the correlated noise. And what we do then, we treat, as Elena described yesterday, we treat this correlated noise sort of like a signal. So and then this is the actual noise. So this is one of the three parameters that we fit in the model. And we assume both of these are Gaussian variables with a set of covariance matrices. So the white noise is just a flat power spectrum given by sigma naught squared. The correlated noise, we assume it's some 1 over f type spectrum, so a power law, where this slope alpha is typically negative, which means that at low frequencies and long timescales, the correlated noise dominates, while at short timescales or high frequencies, the white noise dominates. And the knee frequency tells us like at what frequency, what temporal frequency are these two terms comparable. Okay, so since we assume that they're Gaussian, and we also have assumed the model for these covariance matrices, this is the way to get samples from such a Gaussian distribution. And this first term here is the maximum likelihood term. So if you're only going for the peak of the distribution, we'd only use this one. But of course, we want samples from the distribution, so we use both. We use these terms here as well. And if we go to Fourier space, these matrices here become diagonal. And we can solve this for each frequency, one frequency at a time. So it's very straightforward. And then we get something like this. So the gray here is the signal subtracted data, and then we have the different samples in this colored lines here. So this is very straightforward. Of course, in reality, it's not that simple. So what typically happens if we're pointing towards a point source or a strong foreground in the galactic plane, then our signal model isn't precise enough for us to trust it to subtract that signal precisely. So we don't want, in order to not get some signal leaking into the noise model, we mask out some samples, and that typically happens at least 2 times per minute, because we take 1 minute to go 1 round on the sky, 360 degrees, and then we hit the galactic plane 2 times. But there could also be like point sources and other things. But we have these gaps in the data, and how we represent this in the statistical model is that we just put the white noise level to infinity within here. We don't have this data. But the problem then, we're not longer diagonal in Fourier space, so we can't use this simple solution. So we have to think more generally, and we can think about this as just a general matrix inversion problem, where we have some matrix here, some vector that we want to find, and some fixed right-hand side here. And in Elina's paper about this, one of the companion papers, she shows a very nice method to solve this for exactly this system. And then you get something like this. So within here, way outside the mask, we get basically the same solution as before, but within the gaps here, we get some constrained realization with the higher variance between different samples. So this works, this procedure works, but it's quite costly in terms of CPU time, and so it's one of the more costly steps of the whole Gibbs sampling procedure. And you can see Matthew Galloway's talk today, and also his paper that's coming out for the details on the computational costs. Okay, but it works, and we get these samples. So here is in power spectrum space, we see that at low frequency, the correlated noise is very close, follows the data. But at the high frequency, it's basically independent of the data. It's just an extrapolation of the noise model, and we have the sampling terms that give this thing here. Okay, so that was the correlated noise. The next step is the noise power spectrum parameters. So we have these 3 parameters that we discussed, and we want to sample them as well. And we do this independently for each pointing period, each PID. So it's one pointing period is roughly an hour of data, and we fit it independently for each, or sample it independently for each of them, in order to allow for the case where the noise properties change over time. Okay, so let's start with the sigma naught. We actually don't sample sigma naught, but we fix it using this trick here. So we define this residual, which is the signal subtracted data, and we subtract out the correlated noise. So that's in the model says then it should only be the white noise left. But of course, there could also be some other crap that leaks into this residual here. So in order to not be sensitive, or not let that other crap determine our white noise level, we use this trick here. So we take the difference between subsequent samples of this residual in time, and take the variance of that, because that will only pick up the very short timescale fluctuations in the residual, and give us a robust estimate of the white noise level. Okay, so once we have fixed the white noise level, we can sample the other noise parameters using the correlated noise that we have just sampled. So we know that the correlated noise is Gaussian distributed with this covariance matrix, which depends on Fn and alpha. So we can sample Fn and alpha from this likelihood here. And we do that using inversion sampling. We also impose some priors on Fn and alpha. So we do sample them independently for each pointing period, each hour, but we also use some information derived from the whole mission. And that comes from the Planck DPC team, which derived values for alpha and the knee frequency for each of the radiometers in the LFI, but they derived one value for the entire mission and assumed this was constant. So we use that value that they derived as just a prior, but we have the prior wide enough so that we allow for changes that happen over time. So it's a trade-off between using the information from the whole mission and then allowing it to actually change. This is a nice compromise. Okay, so here's an example of the complete noise model. So we have the signal subtract the data here in blue, and then we have the correlated noise here in orange and the residual in gray here. And the dashed lines here are the noise model. And we see it works, looks to be working pretty well. So we can go on to look at some more results. So here are the correlated noise maps. So what's going on here, we've taken all the 30 gigahertz radiometers and for all the PIDs and added them together into this map. And we get an independent map like this for every Gibbs sample. So all of this is for a single Gibbs sample. And what we see here, we see like stripes along the Planck scanning strategy, which are expected. We don't see much fluctuations in the galactic plane, so there's not much signal leaking in there. From there, that's also a good sign. We don't see much dipole in here. That's also a good sign. But we do see some excessive striping. For example, here in this 44 gigahertz Q, we see some very strong stripes here, and we believe these are related to the gain model, although we don't know precisely, and I could talk a little bit more about that afterward. Okay, so let's move on to the noise parameters. So we, as I said, we sample these independently for each pointing period. And so then we can combine the values for a single radiometer at 70 gigahertz, we can combine the values for the whole mission. And then we can look at this as an evolution over time. So on the top here, we have the alpha, the slope. Here we have the knee frequency. Here we have the white noise level of the uncalibrated data. And here we have the white noise level of the calibrated data. And in the bottom here, we have a chi-squared value. So this is, we've taken this residual and using the white noise level, we've done chi-squared test we calculate the chi-squared in time, and we normalize it so that it should have a mean of 0 and a standard deviation of 1. So this is basically a test of the whole model in the time domain. So if there's some crap that's not fit by the model, it will go into this residual and show up here in the chi-squared. Okay, and these dashed lines here are the results derived by the DPC team. So all these dashed lines down here. And we see that we are, largely consistent with that, but we see also that there are some very clear changes over time here. So in order to see a little bit more what's going on here, we can compare the results we get up here in one of the stable period here with what we get here, like in the middle of this more extreme period here. So we can look at the power spectrum for this radiometer. So here is the average of 10, here is the power spectrum average for over 10 PIDs in the first stable period, and here is the same in this period where we had very different noise properties. We see it's much steeper and also significantly higher knee frequency. So the noise properties actually change very significantly. Let's go on to another radiometer. So this is a different 70 gigahertz radiometer. And we see here that the changes we see over time here are very similar. Like quantitatively, the numbers are a bit different, but we see the same features here. And yeah, let's do another one just for fun. And we see, oh, here it's the same features here that we see again here. So the noise properties are somehow correlated here. And we can also see this on the white noise level. Sorry, we can, if we go back and forth here, we can see that there are some qualitative features that are correlated between them, so they're not independent. So what we can do is to look at this for all the radiometers and all of these parameters and see what that full correlation matrix looks like. And that's what we have here. So here we have the 70 gigahertz, all the radiometers of the 70 gigahertz channel, the 44, the 30 gigahertz. Here is the alpha, here's the knee frequency. So what we've been looking at is this thing here, that the slopes, the alpha is highly correlated between the different 70 gigahertz radiometers, except for this 21M, which is some kind of outlier. But and it's negatively correlated with this knee frequency. But what's also interesting is that it seems to be correlated with the alpha at 44 gigahertz as well, and also at the 30 gigahertz, at least two of these radiometers. So although the correlation here is weaker, we see that there's some common source that leads to these changes in noise properties for the majority of the different detectors. So in order to try and understand this, we can look at some housekeeping data. So the Planck satellite had a bunch of temperature sensors. And I won't go into any details here. You can look at these papers if you want, but I'll just mention there are we have some at the 4 Kelvin stage here and some at the 20 Kelvin stage here. And we can compare that to the derived noise properties that we have found. So here's the average noise properties for all the 70 gigahertz channels. And we see so here's alpha, FNI, and up here we have the temperature sensors. So here is one of the 4 Kelvin sensors. Here is the RMS of the sensor. So within each hour, within each pointing period, there's an RMS, like it measures how large the temperature fluctuations are within that hour, and that's plotted here. Here is the same for a 20 Kelvin sensor, and the RMS of the temperature fluctuations of the 20 Kelvin sensor. And if we look at this as a function of time here and compare to the knee frequency, we see a very striking correlation here. We see that these changes here are related to these thermal fluctuations. And we see it's most closely related to this at the 20 Kelvin stage, but we also see, for example, this spike here at the 4 Kelvin stage, which is not there at the 20 Kelvin stage. We see also that in the data. So that's also related to this stage. But what's actually going on here is that these there's this sorption cooler which cools down this 20 Kelvin stage, which cools down the instrument. And once I got to the point here, it was nearing the end. The primary sorption cooler was nearing the end of its life. So it was adjusted multiple times here in order to extend the lifetime, but then it reached the end of its lifetime, and they switched over to redundant sorption cooler. And that's this very clear drop in temperature that we see here. What happens afterwards is a clear increase in the fluctuations. It's very clear here. And that is thought to be coming from liquid hydrogen in this inactive cooler that's just turned off, sloshing around there, leading to temperature fluctuations. And that was later resolved by heating that up and letting that evaporate. But we see the traces of these steps here and several subsequent steps in order to increase the lifetime of the redundant sorption cooler. We see these things again in the noise properties. So there's a very clear correlation here. And in order to illustrate this correlation maybe even more closely, we can look at this period of adjustments right before this sorption cooler switchover. And we can see this incredibly tight correlation between the temperature fluctuations and the noise properties. So it's not just some vague correlation, it's extremely precise correlations. So there's these changes in noise properties are thermal in origin, but that could lead us to ask the question, so we know that now that the noise properties are correlated between the different radiometers. But the next question is the noise itself correlated between them? Is the noise as a function of time, is that actually correlated between the different detectors, or is it just completely independent? So what we can do is to look at one of the PIDs here in the peak, like where this effect is strongest, and look at it, just plot the data as a function of time. And that's what we've done here. So this is the signal subtracted data for 3 radiometers, one at the 70 gigahertz, one at the 44 gigahertz, and one at the 30 gigahertz for a specific PID here. And we see that the large scale structure here is basically the same. They're extremely correlated at long time scales. So this is sort of a bit disconcerting. So the noise is not independent in the different detectors. But we can ask, is this just a fluke? Is this just a single PID where something weird happens? So we can do a more systematic analysis of these correlations. And what we've done here is to go through every 100th PID and calculated the average correlation within all the detectors at each band. And what we were just looking at was something at the peak here where we have very strong correlations. But we see that for a significant amount of time, we have quite large correlations between the noise in the different detectors. So this tells a very interesting story. But the next question is how large of a problem is this? It's a bit disconcerting that the noise is not independent, but we can look at what time scale is this correlation happening? And we can look at this most extreme case just as an example to illustrate this. So what we can do for this same pointing period that we just looked at, we can take the mean cross correlation of all the noise in the different 70 gigahertz channels, and then see at which frequencies are these correlations happening. And we see here that at the lowest frequencies, the longest time scales, it's almost completely correlated, as we saw. But we see also that once we get to shorter time scales, this correlation drops significantly. And when we get down to the scanning frequency, then the correlations are much, much lower. And importantly, we see that these correlations all seem to go into the correlated noise. So what we do as a check here is to see if the residuals are correlated between the different detectors, and they show no sign of being correlated, which is a good sign, because we don't want this correlation, we don't want this extra correlated noise to go into any of the other components, and this is a good sign that it probably doesn't. It's all picked up in the correlated noise, which was where we want it. Okay, so we studied these noise properties, looked at a few cases for the 70 gigahertz, and then we went on this large tangent for these thermal effects. Let's go back to look at these for the 44 gigahertz and 30 gigahertz as well. So here is an example of the same plot for 44 gigahertz, radiometer 25M. And we see here it's much more stable. We don't see as clearly this effect here, fairly stable here. Here we see these sinusoidal changes here. These are actually from annual fluctuations in the gain, coming from the changing distance to the sun. So this is also a known effect, and this uncorrelated data has an implicit gain dependence that's removed here, so we don't see these annual fluctuations here. The disconcerting thing is this. Here we see that the chi-squared has a very clear positive bias. So this means that there's something in the model somewhere that when we take it into the residual, there's something else that's not just white noise. So let's go and look at one of the 30 gigahertz. Here we see some of the structure that we already looked at for the noise properties. We don't see as much in the knee frequency. We see here the same fluctuations here. That's fine. But we still see this clear excess in chi-squared that we don't like. And this is typical for the 30 gigahertz and the 44 gigahertz, that we have like 2-3 sigma excess on average here. And in order to understand this more clearly, here we have the same radiometer that we just looked at, and we plotted this. So this is the power spectrum of the signal subtracted data in this fairly stable region, and this is the average of 18 PIDs. So we're taking quite a bit of data here. And what we plotted here in these dashed lines are the DPC noise model and the BeyondPlanck noise model. And we see that there's in this region here, there's a small excess. So it's not very visible in an individual PID. As we showed, it was just like 2-3 sigma, and that's not very clear, like when you have all these data points. But when you combine a bunch of them, then you see that it's a very clear excess here. So there's something here that doesn't fit with the 1/f model. And as opposed to earlier, when these correlations were at the very long time scales, this is actually at short time scales. So here, remember, we go around the whole sky every 60 seconds. So that means that 1 hertz is roughly 6 degrees on the sky, right? So this range here is from like about maybe 1 to 60 degrees on the sky. So this is like the main science range that we're interested in. So this is much more varying. And just to look at another case here we have one of the 44 gigahertz channels, and here we see actually it changes over time. So the black line here is a nice one. Here it's an average of 10 PIDs, and it looks pretty nice, fits a 1/f model fine. And then at a later period, we see completely different, as this goes very clearly up here and then goes back again. And here it's back to its normal spectrum. So it's something else that's like added in at these frequencies here, which are crucial frequencies. So if you look at this as a function of time, we can see here the knee frequency is stable and nice, and then poof, at pointing period around 20,000, there's a jump here. And so something clearly happened. And if you look at the chi-squareds here, it's pretty good. And then poof, here. It goes up to like 5 sigma or something on average. So this is not very good. This is not very good. And here, this is the part of the data that we didn't use because we don't like this. We don't trust this. So this was not used in the main run, but it's something that we will study a bit more to try to understand what's going on here. Okay. So in summary, when we do the correlated noise sampling, we use this fairly costly gap filling using CG, but it works great and gives us independent samples each term, each step in the Gibbs chain. We find that noise properties change significantly over time following the thermal environment of the instrument. And we find large correlations between the noise and the different radiometers, although it's mostly in long time scales, and it's picked up by the correlated noise, so we're not that worried about it. But we do find residual issues for 30 and 44 gigahertz, where it looks like maybe the 1/f model breaks down or something else is leaking into the to the noise or to the residual. So these are like one of the main areas we want to understand what's going on and maybe improve on the noise model or something like that. Okay, thank you all.
Thank you, Håvard. Very interesting.